So anyway, this is basically the front screen of the Climate Futures Impact tool we call CFIT. And basically just saying that it uses CMIP 5 as opposed to CMIP 6. In a sense, it could use that. CMIP 6 we don't use because, as you know, it runs quite hot. And or many of the models run quite hot. And there isn't really much different for the base models in terms of their projections than there are in the CMIP 5. So the CMIP 5 is a much more stable and consistent set of analyses associated with climate change. And they haven't changed much in CMIP 6, and so we get the right composition. We'll talk more about that composition in a moment. There's sort of the basic features of how to do the analysis, but we'll get to those pretty quickly. I included an overview tab, and a key feature of this, which I'm not sure many people probably appreciate, is the idea of the confluent risks. So someone may be worried about high temperatures or droughts or precipitation or floods or whatever, and they'll look at that one item. Well, in climate change, they seldom come singularly. So you typically are going to have multiple impactors trying at the same time. And so the idea of understanding what is happening with the other aspects of climate change when you're concerned about one is pretty important, and it's almost universally neglected. And so the idea is that you can finally take a look at climate preparedness. And so as a company, you have an evolving mission that you have to deal with in different operating environments. So it's quite useful, I think, at that. I still consider this a first order local capability. So it's more of a screening tool to help people understand what is actually happening in a country, or what's likely to happen in a country, what they have to worry about possibly happening in a country. But if you need to go in more detail, there are sites that at least give you a better understanding of at least what is happening locally in a very detailed level, sometimes within a 20 square mile area at the present. And then you can sort of extrapolate using this tool to find things out. So going back, this is the idea is to look at coincident joint uncertainty quantification across time and regional. So even though it's a country model, the way the runs were chosen from CMIP were those that had all the same variables, so we could compare across all the areas, all the variables, and all their correlations. That also means that they have the full correlation regionally. So if you set up a run and you're looking at a given country, you can simultaneously see what's happening in the country next door. So there is two possibilities that are actually pretty important to what type of social political environment you're dealing with, or social economic environment. And that the country you are in may look really bad, but the countries around you look even worse. And so everybody's going to sort of want to come to your country, migrate into it. And you may not be in a very good situation yourself. And conversely, things may be bad in your country, and it's actually causing spillover elsewhere. And so the country next door to, say, a place where you have a facility for your company might find itself in serious problems under the recognition that the countries around it are destabilizing. So I hope you'll find this to be pretty fast and effective. And as yet, we haven't found any incorrect results. Now, there's results where we say we've got to put caveats on them because they don't fully correspond to the data we recorded. But when we look at the data that is recorded, it's usually in areas where it's very sparse. And so the results, when you're trying to think of, say, max extreme conditions, most likely there was nothing there to sense it. And the numbers seem to be pretty consistent when we look at other areas. So not saying don't always want to be skeptical, but so far it's pretty good. It certainly is important to interpret the results. That's where it's most easy for a person to get into trouble. One of the things that tends to show, and we're pretty confident in that if it actually shows no problem, it means that the future is probably no worse than the present. So in general, the presumption is that the people in the area and companies coming into it actually understand that area. And so there's nothing that climate sort of adds to their considerations. When it does uncover a concern, it's interesting to note that it's probably likely worse at the local level, because it's often, in general, the model's looking at the aggregate country. and certainly worse and extremes, which we purposely didn't go in the way of modeling one would have become too complicated. And that's an entirely different method. And as you know, surprisingly, it tends to work still pretty well at the extremes. Now, even when it gets to an extreme, and we'll do an example of this, it might not again be an actual problem because in that particular country, it actually is very capable of dealing with those types of extremes. It's actually, I would say, normal, but the particular area is just designed to deal with those extremes. So you certainly need country data. Two, I suggest, obviously not what you'd call the full reference to any country, but at least gives you an idea. The CIA will fact book it now with the PDF. So certainly want to give the caveats. It's not telling you year by year things. So it's plus minus 5 years around a specified year. It's doing things in decades. It has information for the month and it's not by the month. So it's what's the uncertainty within that month. And it's just to help you deal with seasonal concerns. And you select the level of risk you want to look at. It doesn't tell you the risk level that you should be concerned about. The model could do that, but then it would be a black box. Design here is hopefully to make people understand why something is happening and how to think about the phenomena and how it may affect other things. Again, even though it is possible to get a rough handle on local level phenomena, there are certainly downscaling graphical information systems on the web that allows you to look at results at a very local level. And as you've pointed out, it's inappropriate for very large regions that are climatically heterogeneous. We're looking at the country, and so by definition, you're saying that it's heterogeneous. And as you know, there's the full documentation. Certainly, I always recommend volume one. The other volumes are just data if you want to look at them. The other volumes, the only data that I think is sometimes very useful for people is that it has the second order uncertainty. How well do we understand the uncertainty? And typically that is surprisingly small, but if you're really concerned about something, it may be good to go back and look at that second order uncertainty to see if you can even believe the uncertainty that we produced. This notes page or tab on the model just simply goes through all of the different tabs to help give a different idea of what's in the tabs, how to use them, and certainly the basic approach to that. And obviously, we don't want to go through that. The glossary, often people will think that something means something, and there's often multiple definitions on the web in the reports. These are the definitions we use. I don't think any of them are significantly different from what we might consider the mainstream, but nonetheless, there's often the idea of misinterpretation for those. So finally, now we'll go to the sort of main input screen. All of these are drop-down menus, so you can pick any one of the 169 countries, any of the months, any of the years. I'm just going to go down to show you. You can see the historical there. We have 2020. Pick any of the key variables. We picked these because we thought they're most important to actually corporate business and governmental concerns about what's going to happen in the country, economic concerns. So that's what we've picked there. On the others, you can pick the high and the low. So when we look at the exceedance probabilities, they'll go between 0 and 50%, because it's a question whether you're worried about something being higher than what it is normally or whether lower at that percent level. So we're looking at Nigeria right now. One of the things that people often don't think about is that when you look at the CMET results, there's a lot of noise in them. And as you actually try to interpret them, it ends up that the noise and probabilities you see not only have a temporal interpretation, but I guess I'll call it at the moment interpretation, saying that this is the probability of this happening at this moment. And so here's the idea of giving what your odds are. So obviously something 50-50, there's a 1 in 2 chance you'll see a number higher or lower than that in the current year. But when you're down to a 5% level, that means you've still got, in a sense, a 50%, well, here, a 40% likelihood that a 5% exceedance probability will be seen in 20 years. That's the lifetime of a lot of facilities, and certainly infrastructure if you're trying to build it to deal with climate change. And certainly one can change Some secondary considerations that we look at mostly associated with labor in terms of what temperature units you want to look at. Um, Whether you want to compare it to history or you want to compare it to the present, like 2020, and the idea what type of, if you're actually looking at labor concerns, what's the intensity of the labor you're concerned about, and whether they're working outside or inside. So
And
anyway,
when,
this is just
and wait, two quick things. One, when I used to work at DNV, we would talk about, what are we designing? Not we, but what was DNV designing offshore rigs for? In terms of probabilities of rogue waves,
yes,
and those rigs are designed for 1 in 10,000 year waves. Uh,
yes.
so it's they're not using averages. Um, can you, one thing that I want to make absolutely sure I'm understanding, for example, for the referent variable of max temperature, um, can you just describe to me, exactly what that variable in terms of the monthly data sets as opposed to daily variability? Can you just make sure I understand what that variable means, and that using that variable is telling me?
All right. So if you're doing the max variable, it's stating that's the normal variable of concern, and the model will reference everything else, every other variable to that referent
And
variable.
wait, I'm sorry. I may have misspoken. I meant the max temp reference variable.
Yes. I'm sorry, I meant to say max temperature.
Okay. Okay.
And so you would pick whatever one you want.
Okay.
It's that max temperature is actually the average maximum temperature over that month.
Over the 30 days or whatever of that month, it's the average maximum temperature. That's what I thought. I just wanted to double check.
Yes. So it's not
Okay.
the maximum
Right.
temperature,
Right.
but you can
Right.
sort of, we will fake it, and you get to see what that looks like in a sense. If you pick one day out of 30, then it, in a sense, is the maximum temperature for that day. It's a rough estimate of it.
The average maximum temperature is a good estimate of the maximum temperature for any given day.
You can do that by setting the probability down. So rather than being for a month, the probability is measuring it for one day of the month. So the maximum temperature occurs about 4 hours, and it's 30 days. So that ends up to be a probability of about 8%. So if you look at the 1% probability, you actually get the maximum
Ah,
temperature in
I
that
see what you're
country
I see what you're saying. Okay.
that day. And if you want to say, well, this is still the maximum temperature for that country on average. So it's average now over the country, the maximum temperature you report in that country on average. But if you wanted to say, for example, go one step further and say, well, the highest temperature is maybe in 10% of the country. So you go from 1% down to a tenth of 1%. And then you actually have an estimate of the actual extreme highest temperature in anywhere in the country for that day.
Excluding natural variability.
Or we're just doing probabilities.
We're doing modeled probabilities,
Yes,
but even around those numbers, you would expect sort of random natural variability, right?
that's right. So this is what we might call the expected
Right. Okay. Oh,
highest temperature for that day at a particular
exactly.
location.
Exactly. Okay. Thank you
So
very
that's
much.
good point. Now, I don't overly trust these numbers because we are not using in this work generalized extreme value distributions. Now, it ends up that the Weibull distribution for wind is one of those. So it actually does have some meaning there. Typically, we do not think it is credible in the normal distribution, and only partially credible in a gamma distribution. But nonetheless, in general, the model tends to do quite well at least giving you a handle of what type of extremes you might want to worry about.
Mhm.
And if it gives one that's pretty high and it sounds crazy, then it's just really say there's at least a potential issue there that you want to seriously consider. Is we haven't found it to be laughable in the sense that it says something's going to be 53 degrees C, for example, and the highest you've previously seen is 43 degrees C.
Right.
Um, the next year you might see it at 51, and suddenly at 53 looks like we maybe should look at this a little bit more. So I'm not saying the model's correct, but as a screening tool, it's sending you in the right direction.
Got it.
All right. So now here's the visual results for this Nigeria. We picked precipitation. And in this particular case, we're looking at the 10% exceedance on this radar curve. And each of these have the different temperatures and the axes, where the blue is the historical value. The purple is the mean of the future value, which is here 2050. And the black is the exceedance. Now, we got to remember that the mean is not, other than normal distribution, the mean is not the same as the exceedance probability.
That's the median.
So it's correct in saying what it is, which in this case, we're going to have a large amount of runoff, and it's in what's called a delta ratio. So it's going to be on the order of twice of what it was historical. So it's out in what we might call the red zone. We'll also see that precipitation is dropping despite runoff increasing, which is an interesting phenomena, is that if you don't have a lot of precipitation, the ground packs, and so it can't absorb water. So when you do have rain, you're going to get a lot of runoff. And so that's an interesting result that people would sort of think this is crazy, that you got less precipitation and more runoff, and the model's helping you understand that.
Right.
And of course, in that process, you're getting less soil moisture. So whatever, if you're in a country that is heavy on agriculture, whatever you planted is not going to grow very well. And
No.
the water is going to lower and run it away.
Right.
And what's worse is that if you look at the wind, it's getting into that zone as well. And I think, and this one we'll look at the numbers, it's about 1.25, what the normal number is. Well, the impact of wind is the velocity squared. So your topsoil is being blown away as well. So you've got, when you're worried just about runoff, all of a sudden you now realize you've got a composite picture of an understanding of what's going on and how to prepare for that.
Right. And George, I don't know whether you remember this or not. Did I, in my videos describing this, did I screw up between the mean and the median?
No, I don't think you did.
Okay.
I
Okay.
didn't see anything.
Okay.
So we're fine. But for people to, and certainly if you're talking about a normal distribution, it makes obviously no difference. But,
Right.
certainly in precipitation, it makes a big difference. So another thing let's look over layer productivity ratio, and notice that in this situation, the productivity is down to 60%. So this is outdoor productivity. It says outdoor for labor. So if you were, say, worried about oil rigs in Nigeria, people working on the outside of the rig are going to have problems. Even in the ocean, although it's a little bit better place. And even though it's 100% now, the idea in the future is that the humidity and temperature together, being it's nonlinear, actually cause a combination that brings that down. Now, the productivity is going to go down, at least the claims according to the data that are available and pretty much well agreed upon, but you're not at the physiological limits. So people are not going to be able to work quite as well, you're going to take breaks, et cetera. But the human body is actually still going to be able to tolerate once they stop working, that they're okay. We'll do possibly some examples here where
Right. And there's very little change in that physiological limit number, but a significant change in labor productivity. Right.
That's right.
Okay.
So here it gives the numerical analysis, so you can see how different things down at the bottom are here than what they would normally be, and the ratio is pretty much more meaningful to me in terms of the temperatures and the changes. But you can actually see the absolute changes on the other side of this, and you can also see what's the cause of the human impairment in terms of the wet bulb temperature. And then just a statement of over here what you're talking about. So even though you're only at a 10% probability, there's a 65% chance that's going to occur over the decade. And when it does occur in about 10 years, it's going to come back. So you can get a lot of information off of that. Here's when you want the actual detailed data. So it has the variables at the exceedance probability, what the distribution is, its year, these are the parameters that define that probability. Here's what the exceedance probabilities all are in their relationship. So you picked the um, precipitation as your variable in this case. And so that's at the 10%. And these are what all the exceedance probabilities that will occur expected for all of the other variables. So you can see that interaction and then what those look like in real terms in different units of measure to help people get a grasp what that actually means. Here's what the future on average looks like, which helps people understand how different are these extremes than. And actually go off on a little tangent, which you're used to when we look at the exceedance curves in a second, is that they rotate over often. So even though the future mean is just moving slightly over, you'll sometimes find that the exceedance probabilities are really getting extreme very fast. Now, conversely, you can have the problem where the mean is moving over, but because of the climate, the variation is declining. You're not getting the winds. You're out of the jet streams. You're not getting the precipitation. And so suddenly your extremes start to look like the mean. And so it's very, I call it enlightening, but it's sort of unusual to see and for people to recognize. Often we sort of think that just because the future is going up, the extremes are going up, or the high exceedance probabilities are going up, or low exceedance probabilities. And that is not necessarily the case. And then, of
And
course,
in what is your sense around the idea of whether in general variability will increase over time?
honestly,
Um,
so we have some curves to show that, and it's different for each country.
okay. Yeah. Okay. And you pick for each variable, you have picked the distribution that you consider most appropriate.
So we didn't. We uh, took the data, we downloaded the full CMIP5 data set, and we brought in experts on precipitation, temperature, soil moisture, et cetera, and said, what are the probabilities you use, just like the probabilities you use for the road waves in the oil rigs? What curves describe those probabilities, those distributions of that data via real world experience?
Mhm.
And those are what we applied. And so those rationalizations are then in the volume one document that describes the creation and basis for this for CFIT.
Okay.
So all good questions. Here's the volatility. And so this does not represent 100 years. You can pick any 10 years you want, and this will show a possible, I call it a motif, but a pattern of volatility you'll see. One is pink noise. So whether the volatility is associated with something like the El Nino, El Nino cycle, the ENSO cycle, versus the idea of whether it just randomly occurs year to year. And you can, and so if you're designing something, can you see this pattern? By definition, there's a 1 in 100 chance that the highs and the lows will occur. I mean, roughly speaking, there's a 50% chance that there's a 1% chance that this will occur. And you can go through and by hitting it function F9, see all these possibilities. And so a person can start to think, whatever I'm designing or concerned about, will this work? And you can certainly, this is proportionally how variation. So, dummies are varying by a factor of two, but you can actually look at in terms of absolute terms, and you have to sort of know what the units of measure are. So we're doing precipitation. So this is probably millimeters per day. So here's precipitation, and here's what the mean actually looks like over time. And notice it's varying, which you expect part of the ENSO cycle. And so this means that you want to use pink noise. So here's the trend line, but it's varying. So you want to look at the pink noise. And here's your standard deviation. So is it getting worse or is it getting better? Well, the variation is going to be high, it appears, when I have an El Nino cycle. When I have a La Nina cycle, it's going to be lower. But overall, it's not really increasing that much over time.
Right.
I looked at the average temperature, it's pretty smooth. So this is a white noise phenomena as to what the temperature is going to look like. Now, on the other hand, if I look at the standard deviation, it's not terrible for temperature. But as I get out in the future, I finally, in a sense, even these models sort of cross the tipping point and the variation starts to become very high.
Right. Right.
So we have this for all of the different max temperature. Wind, as we respect associated with stroke, is not as affected. So you could use sort of a difference between white noise and uh, pink noise. And actually, in most models, the variation in wind goes down, not up. And this was sort of thought pretty crazy when we first came up with these results because there's more energy in the atmosphere, should be more wind. But I think you've hopefully read or saw several giant cars that they're calling it the great stilling that is occurring. And so the model actually reduced that in a sense ahead of its time.
Yeah.
The soil moisture is obviously associated with which a different cycle because it has to dry out, a little different timing, but it's still up and down. And certainly, as you would guess, very much correlated with the precipitation. And then finally, the humidity of how that occurs and the trend down. So actually, in Nigeria, the temperature is going up, but the humidity is actually going down. It's not a terrible drop. So the net effect is still that you're getting these problems with being able to work, and the standard deviation is slightly increasing, but it actually wasn't it actually increased over history, but now it's going to stabilize for a while and then taper off again. This is the model. And then evaporation, again, associated with both soil moisture and precipitation. So you're getting the compounding effect. So it has a very exaggerated cycle. And then the runoff, which is the combination of all these things happen, actually doesn't because you have counteracting phenomena going on.
And George, if you go back to the humidity for just a second.
Yep.
Why is that standard deviation 9?
This is in absolute terms. So if it's 100% humidity, 60% humidity, the standard deviation is 8% humidity points.
Okay. So it's a different scale than on the others, which are okay.
Yes.
Okay.
So these are in temperatures.
And some of them were, 0.0. Yeah. Okay. I see. Every single one of them is totally different in terms of the standard deviation metrics.
Yes.
Okay. Okay. And just a quick question on the volatility. So that is volatility, that is expected volatility around the expected 30-day mean
Oh, this is actually, yes, it's around the 30-day mean.
But does that account, does that account sort of for random natural variability or still not?
Yes. So this is doing natural random variability.
Okay.
Yes.
Okay. I wasn't 100% sure on that. So that's good to know. Okay.
So yes, you're actually saying it's including the natural variability. So this is a really very realistic representation of what the possibilities are. Probably there's no year that actually looks like this, but each of these are a representative possibility that could actually occur.
And can I generate this volatility at the 1% exceedance or
No, it's just across the mean. So in a sense,
okay.
You're saying this is 100 years worth for April.
Right.
And so you're actually saying that any one of these peak points have basically a 1% probability.
Right. And at the daily level, repeating our prior conversation, it could be substantially different from that.
Yes. Yeah. So this is the average monthly value.
Right.
So was that original caveat. Whenever this shows and you think it's bad, there could be a chance it could be much worse than that.
Right.
So if you can't even design for these types of levels, I mean, all of a sudden this curve or this curve, so this is precipitation, where you don't have precipitation for that month, or here, in principle, it's saying for a whole year.
Yeah.
And here for multiple years, you're basically at zero, and you just simply can't tolerate that.
Yeah.
Then you're in a problem. Now we may take a look at the Ethiopian Renaissance Dam, which you may be familiar with. So it blocks off the Nile. Ethiopia built it.
Oh, okay. Yeah. Yeah. Okay.
And so the issue is whether if something bad happens to the weather, will Ethiopia decide to just hold the water
Right.
and not let it go to Egypt?
Right.
And Egypt says, well, we're buying a whole lot more jets to be able to go to that dam and blow it up if that happens. So So here's a situation where you could have two really bad years in a row that would say the water's not going to be there. And so what does that mean? And how do you sort of need to think about that? Say if you're
Right.
worried about security issues or
Yeah.
doing
Yeah.
business in
It's the second and third order things that are going to bite you. Yep.
yes. So here's the ellipses. I'm going to make this a little smaller. Well, make sure it's big for now. So this basically takes each variable by itself and it shows the relationship of one variable to the other as if it was normally distributed. It's really tough to do this with the other um, distributions, but it still's pretty good when it's out on the edges. When it gets to an edge here where something goes to zero, then this actually will distort and balance down. Each of these rings represent a probability. So you're at this ring, say for example, for precipitation and a minimum. Well, that's not probably very interesting to people. Precipitation and evaporation. I'll take for the moment. Um, inside I'm trying to find one that's actually interesting to look at rather than uh, this. Um, oh, I guess actually this one was. This is wind speed. So actually, here's on this one for the wind speed. I'm going to make it a little bigger so we can see it. So here's for the wind speed, and here's the mean in 2030. And when you're inside this curve, it means that wind and precipitation there's only a 30% chance that it will be outside of this range. And any um, point within this ellipse potentially is equally probable in a sense. And you can work your way all the way out to 5%. And you can see that if the maximum wind does not change very much, even though the precipitation can change a lot. And I don't know if precipitation this would be totally useful. It just says you don't need to worry about the wind extremes as much as you do the precipitation extremes. And if you want to see where is it going in future, this whole ellipse is moving towards less um, precipitation, which is what is true in Africa. It's moving from the west of Africa to the east of Africa. So that all corresponds. And it's rising. So it's going this way. So wind is going to be consistently stronger on average in Nigeria. And so here are the exceedance probabilities for Nigeria. And I think I want to go back just to the input to exaggerate these a second. So we can sort of see what the things will look like. And so back to the exceedance curves. So in reality, precipitation is not changing very much in its curve. It's not changing very much. So in a sense, Nigeria always had this problem of how precipitation would affect it. And if you look back in the news items, it actually has had areas of drought. Here we can take a look at humidity, and you can see that the curve is rotating and it's rotating counterclockwise. So there's going to be less and less chance of low humidity in that area. Wind speed is doing the same. It's rotating all the way over. So in a sense, you're going to have hardly any extremes. Well, I mean, it's still there being exaggerated, but it's rotating. So you mostly just have the mean temperature. And then when we look at the max temperature, you can see it's rotating clockwise. So you're going to have much higher extremes, which are rising faster than the mean is rising. I mean, the median is rising. So these are, to me, always quite useful to get an appreciation of how the change in what you're looking at, what it really means, rather than to say it's crazy. Especially if it says well, history has happened a lot, like right here for the last wind, or whether it's something you really need to worry about.
And I wasn't 100% sure what you meant by rotating, but now I see what you mean in terms of sort of the
Yeah.
clock. Yeah.
Yep. So this is rotating out from this curve.
Right.
This one's rotating into the curve.
Right.
So it's actually rather a neat phenomenon. And so we've already gone through all the distributions. Here's where the calculations are actually done. It's called the analysis tab. It's sort of hidden a bit farther away. And so you can actually see the equations that actually produce the results. So you go back and sort of think whether you would like these things. And far to the right is actually the ability to go to climate EXP or whatever and take a look at what has historically happened for the maximum temperatures, and you can actually put that in, and then it will actually do a better job of telling you what the extremes are.
Mm.
And here's at the local level. I mean, I think climate EXP goes down to the 20 square kilometer grid space. So you can really hone in if you want. Even at this point, obviously, it's still a first order. Well, it's now a second order estimate, I suppose, but still not one that you necessarily believe is true. You've refined it, so it's now, instead of being um, homogeneous nationally, it's still um, temporally homogeneous locally. So you still have a homogeneous aspect to it. So now, if you want, we can go through a couple of variations on this. So anyway, Nigeria does not have a problem, um, even though it would appear to via these results with runoffs, because it's historically had that problem. So it's not new. But it does cause significant problems because Nigeria is set to quadruple its population by 2050. So the impacts of this are going to be quite large, as we're seeing, and certainly in Bangladesh and Pakistan
But
these
if the
days.
delta, George, if the delta ratio has increased so much,
It hasn't increased over history. If I go back and I take a look at history, and we saw that when we did actually saw that in the exceedance curves, it's gone up, but it was always in the red.
okay, okay, huh, okay,
So anyway, this is, I mean, a good discussion we're having, because it sort of shows how you need to think about something when you see a problem. And so this
right,
is not as big of a problem as you might think, other than that there's more people. So it will be a little worse.
right. But you can go using the exceedance curve, you can get a sense that, yeah, maybe a little worse, but there's no change of state, so to speak.
Yes, compared to history. So that's why we put the historical curve there. And so it's always important to compare to history what's going on. So, um, whenever you do the analysis, those things have to go on in your head. It's easy for someone just to press a number and get an answer, and on one hand they're misinterpreting it, uh, but it's mostly because climate change isn't easy. And so, once you sort of get used to the idea of always cross-checking with history, and and a particular problem, actually just doing a Google search and say, is is there any news about this being a problem? And if there is, well, then it's not a big problem. On the other hand, there's no news, then this is probably meaningful in the sense that there's a problem.
Yeah.
All right. So think I'm going to go to take a look at some here, see if they like that you would find interesting, possibly. I guess I'll start off by staying in precipitation and go to Thailand, because if you remember, Thailand several years ago had a flood, and we no longer had computer chips for a while. Sort of the
Yeah.
same as
Hard
happened.
drives. We didn't have hard drives. Yeah.
Yeah, didn't have hard drives. Where's Thailand here? And
And yet the attribution scientists have said that was not a climate change event.
it's possible that that was not a climate change event. I guess I have to take a look at that. I think July is considered the monsoon reason for that. And I guess we'll stick with the 10%, and I'm going to go high because we want to go flooding for this rather than shortage, and see what the visual results are. And runoff is off the charts. And so certainly this is a big stressor. Knows also in 2050, when you are concerned about precipitation, not temperature, productivity is dropping, and you're starting to at least get into the yellow range of your physiological limits. And in this case, you'll find that you went through everything, that the runoff really is a problem. It's about 12 times larger, I think. So, and now we're going to just switch to, in a sense, a neighbor. I'm going to take a look at Bangladesh and take a look at what that looks like. And so it is saying the extreme precipitation, extreme runoff. So it's even worse And notice that because of its heat and everything else, what the layer productivity looks like in the middle of summer.
Yeah, there is not. Yeah.
And you
Okay.
can't even be outdoors. I mean, you can be, but you've got to limit it. So you get some really, I guess I'll call some significant uh, problems in this. And so generally, as we already know, it's the flooding and such, that there's intense migration pressures at this point. And so to think about where you're going to move that many people, which pretty hard. Now I want to pick one which was less interesting in the didn't have baggage before, but Ukraine, which then was just a nice qualifying uh, breadbasket of the world. And I'm going to take a look at soil moisture because that's very important to Ukraine. And I'm going to pick August, so you're just getting ready to harvest. And let's take a look at the visual.
And did you want high or low?
Yeah, you're right. That's what I messed up. Thank you. Want this one moisture, but want this low. Oh, good. So looks pretty bad. There is absolutely no runoff. So this is sort of saying the rivers are all dried up. There's no soil moisture. There's nothing going on. Now, if we take a look at this and go back to, so everybody wants to scream that this is the end of the world for Ukraine in 2050. But if you look at it historically, pretty much the same curve. So the soil moisture does drop during the harvest season, not a big deal. And in Ukraine, it has this wonderful soil. That's why that's a growing basket. It holds all the moisture. So even when the river is, in a sense, flowing, it's just sucking the moisture into itself.
Right.
So there is no problem here whatsoever. And by looking at history, you immediately see that as being the phenomena that occurs. There is I'm not going to go into it, but the idea is knows that the temperature is actually going up on the minimum temperature side.
Mhm.
And for some crops, you need to have a low minimum temperature. So you do. So it's actually sort of says, maybe I should stop looking at the soil moisture and take a look at the minimum temperatures. And in some
Right.
countries, that's important. In fact, in Turkey, that becomes an important aspect that Turkey, if we would do that analysis, will lose a significant number of their crops. I think that's in the volume one report
Mm.
because its minimum temperature is getting too high. And so something that people don't worry about very much. Let's see if we've got any other ones that are might be, although the fun that's sort of fun to see and to get them. I'm going to go to Oman, which we already know is going to be uninhabitable. And I'm actually going to go back in history. I think I have this for July and maximum temperature. I think I want, let's see, and we want that high. And I'm just going to first do the bit since I've done this. So for this, layer productivity has gone to low and you have crossed the line, 35 degrees. And this is wet bulb temperature. You cannot be outside. So now I'll go back to the historical and I'm going to maximum temperature, but I'm going to go to what percent? Yes, 1%, which will represent 4 hours of a day. So it's basically 4 hours of a 30-day month. So it's basically 120. So it's pretty close to what 1%. And I'm going to go back down. I think I'm going to go to value results and we find the maximum temperature and see if I've got this still uh, right. So here is the July at 1%, which is 45.7 degrees is the maximum temperature. And the actual recorded was 46 degrees. So now go back and hit this for a tenth, which would be the highest. So that was the average temperature for the country as reported. And now this will be the peak temperature, the peak in the country. And it's 47.6 is what CFIT says. And the actual number was 48 degrees. So very close. Now it can go beyond that, but um, it intends that CFIT can, if it's going to err, it usually errs at the temperature is higher than what it says it is, but it's still indicative that it's something to worry about.
Okay.
So I'm going to do one last one, and then we're done.
Okay.
And this is going to be, I think I'm just going to look at Ethiopia, just to show you a trick here that you can use or a person can use. If I take Ethiopia, and I think I want July again, and I'm going to do 2030 because that's the importance for the dam to be filled here. And I'm going to take a look at the average temperature, and I'm going to use the 50% exceedance probability. Now, here occurs all, fall together on this.
Hmm.
And now, so it looks as if everything's going to be just fine. And so even though we um, see it close, there are some variations, but they're not very much. So it says on average, the dam is going to be able to be filled on average. Of course, if we look at volatility, it actually looks like it's pretty smooth as well, at least for that month. So even though you can have at different times of the years some rapid variations, if I had to worry a lot about what's going to happen in terms of war in the Middle East due to the Ethiopian dam, this analysis would say, probably don't worry about it very much. Now, I'll quit there. There's another analysis we could do, which would take a look, for example, Burkina Faso, and then see how bad it is, but then go to Mali and the countries around it and see what their condition is. And you'll find that in the situation that Senegal all of a sudden becomes the hot spot, in a sense, to move all of the population. It's actually cool. It's next to the ocean. And so these other countries get into really bad situations, Mali already being destabilized, but Senegal does not. And so it becomes destabilized by its neighbors.
Right.
And so that's a interesting thing when you look at it across the countries, but I don't think we need to do that because I want to take more of your time. So anyway, that sort of is a summary of CFIT.